Record. All right. In case you don't have the link for whatever reason, if you wanted to try to join the Zoom, just turn your audio off, and that's the Zoom link. You might be able to see my screen better than you can see on these, is the thought. So it's up to you. I also record it, so you'll have my screen on the recording. All right. So how did the homework go? You were just getting Hello World working on online GDB, went fine for everybody. So now you have a working software development environment that I can now start giving you difficult stuff. Well, relatively difficult relative to what you're learning in class. All right, so oh, and just a reminder, and I'll probably mention it again on Thursday too. So remember, next week and the week after, you're going to have a guest lecture here talking about quantum computing programming, quantum programming. He kind of knows the level that you all are at. I will probably also be creating some lecture videos of stuff I would have been covering in class during those days. And then I might give you some assignments, but I will take into consideration that I'm expecting you to watch those videos outside of class, since you're already kind of getting double lectures. So any assignments I have you do, I'll take into consideration that, hour of video lecture or something that I'm expecting you to watch, just so we don't fall behind because I'm gone. All right, go ahead.
Are there any tech talks coming up?
That would be a Ross Jacobson question. I don't know. As soon as I know, I'll put it up there. So what he's referencing is historically we do about three tech talks per semester, where we bring in businesses from outside the university or people in the tech industry to come and give a talk to our students. Typically, this is around the people we invite are folks who hire interns from here. So not only are you learning about what their business do and what their business does, you're also introducing potentially your future employer. So we encourage students to maybe bring their resumes, that kind of stuff. So past folks who have come, Acuity, it's one of them up in Sheboygan. Acuity, you're an insurance company, and they might come off. It sounds like insurance companies are kind of boring, but actually Acuity is kind of like the Google of the Midwest. If you go into their offices, they're the one up in Sheboygan that has the gigantic American flag outside. If you go in there, they have rock climbing walls and like a working Ferris wheel inside the building, and $1 zillion worth of like blown glass hanging from the ceiling, kind of cool stuff. And any case, so they've historically hired some of our very best students as full-timers. We probably have something like 15 or 20 former students who work there full-time still. And sometimes what we'll do, in the past, we've done back-to-back tech talks, where the first week we'll have the Acuity managers and stuff come here. Then the next week we'll have like a round table with our former students, where you can ask them the real questions about what it's like working there, yada, 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 that stuff. Most of them seem pretty happy, so I think that's not a big deal. Acuity also paid $300,000 towards the renovation across the hall, so I think they value us too, but we very much value their money. So, and them, but that renovation didn't happen without Acuity's help. So if you're on esports, the esports team, it's the Acuity Esports Arena. So it's because they put the bill. But yeah, so tech talks I think are an important thing to get involved with, and I'll even mention it related to that. Historically, I've made tech talks like a requirement in classes, and you had to write like a little paper based on it, or there was an alternative assignment if for some reason you worked and couldn't go to it. Similarly, we have like hackathons here on campus, like the first one's tonight. How many of you are doing the hackathon tonight? Okay, so we got 2.25 people. You had to be signed up for it already, because they sent out an email this morning with the teams. Okay, and we've multiple times we put out on Slack the sign up things for it. So what I'm telling you is that 20 or so of you are missing out. I know it's extra time outside of your schedule. I realize some of you might work and you just couldn't have made it, but those experiences, you will learn way more in those than you're ever going to learn in the classroom. I just promise you that. Every single person who's ever traveled around with us to the hackathons has gotten very high paying jobs and doing some really cool stuff. Because you're only going to learn what I'm spitting out of here in the classroom, and then you're only out of that, you're only going to retain so much. When you're at these hackathons, even as a completely new programmer, not really going to be able to probably give that much to your team other than maybe doing some research or something like that for them. You're going to see what a real software development lifecycle looks like, and you'll start off as basically a non-participating member, but eventually you'll be a team lead because you're going to be learning this stuff over the 4 years. So keep your eye open. Usually we do 2 to 3 hackathons per term. It looks like Ross is doing kind of shorter hackathons this time. So today's is, I think, it's 4 hours, which is pretty short for a hackathon. Historical hackathons that we go and travel to are 24-hour events where, they have like sleeping and, they bring food in and stuff. Go ahead.
Can you watch it online?
Well, it'll be located across the hall physically. I think there is, we have a couple of teams that are remote because we have some of our grad students who are also doing it, and they are in, some of them live in Chicago, so we set it up on Zoom. But I mean, you can contact Ross Jacobson about the Zoom link, because perhaps it's actually the same Zoom link I gave you for my class here is what they're using. But I would assume around maybe like 7:30 p.m. or so is probably when they're going to be doing like presenting what they created during their 4-hour something or other. That would be my guess. But if you're interested in kind of watching what they make, I'm not sure what the topic is. I had suggested to Ross maybe doing something with the ChatGPT API. So writing some sort of little utility or something like that that leverages ChatGPT programmatically behind the scenes to do something, kind of just to getting creative juices flowing for what things you might use an AI to accomplish. But so if you're not participating in it this time, you missed the boat. But this is only the first of many during your 4 years here, so I strongly encourage you to get involved in those things moving forward. You're paying a lot of money for school. You might as well take as much experience out of it as you can get, because you're not going to get that much out of the classroom. I mean, we're here for an hour and a half twice a week, and 2/3 of the stuff I'm saying is in one ear and out the other until you go back and do your homework and study this stuff. So hands-on experience is a big deal. So please take advantage of those things. Okay, other questions before we dive in? All right, so like I said, next week, I'm here this Thursday. I leave Tuesday morning next week, so I won't even be here for class on Tuesday, but Waleed will be here. Both lectures next week, the 2 lectures the week after that, giving a crash course on quantum computing, quantum programming, kind of just an introductory type thing. He knows where you're at skill-wise. But then I'm also going to be doing some video lectures so we can keep progressing while I'm gone, and I'll take that in consideration for the time I'm expecting you to spend outside of class for the homework assignments, since they'll probably be like 50-minute video lecture or something like that, depending on what topic I want to cover. And then I'll give you a little assignment associated with that, but I'll try to keep the whole time footprint of what I'm expecting you to do outside the classroom at a reasonable level. So I appreciate you tolerating me being gone for a couple of classes, but now you're getting double lectures, value add, and you don't have to put up with me in person. All right, so we started talking about actual coding last time, and we went back to one of our earlier slides that I kind of like talking about, how human beings solve problems. And I mean, it always comes back to this. We just have to keep reminding ourselves that a programming language is a tool that allows us to tell this guy what to do. That's all we're doing. All right. I had several grad students come up to me yesterday, and these are people with industry experience and things like that, and they'll say, oh, I have 1.5 years of Java experience or something like that. And in their mind, Java is a skill. It's not, it's just a language, right? So all of you in here have 18, 19, 20 years of English experience, right? But the reality is you have 20 years of experience in interacting with human beings. That's the actual skill you have, right? You've learned how to use the English protocol to exercise that skill. But some of you in here know other languages. Almost every one of my grad students knows at least 2 languages, which is 1.5 languages more than I know, right? At the end of the day. Most of them speak Telugu, which is the language in Hyderabad, India, and then Hindi. Some of them will speak Urdu. So some of them have a minimum of 4 languages they know. But every single time they're using one of those languages, they're talking to a person. So your mindset, the skill you're using to interact with the thing you're interacting with is the same. Same thing's true with programming languages. Doesn't matter which language we're using, whether it's English or whether it's Spanish. If you're talking to a computer, you're going to be using the same problem solving, the same mindset. That makes sense? All right. So I like to look at it all programming. Well, the way human beings solve problems is we remember stuff, we ask questions, and we do repetition. 100% of programming languages have facilities for those 3 things. So if I threw a brand new language at you that you've never seen before, and you already have the skill set of telling a computer what to do, you can say, well, how do I remember stuff? How do I create variables in this language? How do I ask questions, if statements? How do I write loops and functions, procedures? And when you have those couple of things in your pocket, you can immediately start writing a large number of programs in that language instantaneously. You throw that on top of, you have a working hello world program in the language. Now you have a program you know how to run, and you know how to remember stuff, ask questions, and do repetition. Probably 90% of all programs you'll ever write uses mostly that stuff. You know, it's just that last 10% that uses some special sauce where maybe you're contacting something external like a ChatGPT API or Google Maps or whatever, whatever it is. So programming languages are far more accessible than natural languages. I'm terrible at learning new natural languages. Like I once tried to learn Spanish because they made me in school, and I barely can order at Taco Bell. Just those things don't come easy for me. I mean, most of it has to do with I'm thinking my English background. I speak well, but my grammar and stuff, I probably learned the fake grammar. But like in high school, remember you had to do the sentence diagramming? Do they still do that? Sentence diagramming in like the English class in high school? Or they just threw it? Don't even know what I'm talking about? Oh, see, back then we used to have to like prove we knew how English worked. I was just randomly writing crap in there. I had no idea what I was doing. So yeah, so take that for what it is. But anyways, I'm terrible at learning natural languages, pretty decent at learning programming languages. And the mindset that I go into it with is this mindset here. So this is coming out of my own personal experience from programming since I was 9. Learning new languages you can do in a weekend once you have the programming skill set, once you know how to boss this guy around. All right, so we introduced ourselves to an IDE last time. We're using online GDB. If you want to use something different and you're familiar with GitHub and want to provide me a link on GitHub with however you're doing your homework, that's fine. But I'm not going to support all these different IDEs you might use. So if you don't know what I'm talking about, use online GDB for now. Eventually, those other skills come in, but we want to focus on the coding here, not getting some sort of development environment set up on your computer and all this other stuff. All right, so we're using online GDB to do all of our programming. And we looked at some examples last time. So let's just jump back to that and continue to explore these things. I think I saved it, didn't I? Last example, nope. Super Ninja. No, maybe I didn't. That's okay. Go back here. So as our model, I'm going to choose my language. Make sure you choose C++. It probably, for what we do in here, probably wouldn't matter which of these C++s you choose. These are different releases of C++ because it's an older language, so things have changed over the years. I always just pick the normal C++, but we're doing pretty trivial things in here. So there's your baseline, hello world, hit run, blah, blah, blah. You see it work, there's your homework assignment, right? So everybody has knows how to hit the run button. All right, we saw last time that we could create some variables. I thought we had slides for that. Didn't I create something not save? Right. Oh, okay. Well, I'll just recreate them here. So for variables, so this is our memory. The syntax is type followed by var name equals value. So we could do something like int a is equal to 5, where int is the type. We're going to store an integer. Similarly, you can say float f is equal to 3.14. Actually, let's use decent variable names. So we'll call this float pi. So get the pattern. What kind of value am I holding? What's the name of the variable? Because I'm going to reuse it later on and it is case sensitive. And then what's the value that I'm going to start it off at? It's a variable though, so it can vary in value. We can change the value of it. Okay. And I think I probably showed you last time. Here, let me save this to make sure that's working. I can do something like int a is equal to 5. And then I showed you how to output stuff. So I can do C out A. I think I didn't do that last. We'll just leave it like that. So we get our 5 printed to the screen. If I change the 5 to a 7 here, I don't have to change my print statement. It now prints whatever it's remembering. If I store it as a 7, print it out as a 7, then change it to a 13. And then I print it out again. Now you'll see the new value. So A is 7, output the 7, change A to 13. Notice that I'm not redefining it. You only need to put the type the very first time you say, I want to remember something. I'm bringing it into existence. Okay. So I'm remembering this little place in my mind called A. I'm storing a 7 in there. And then if I ever want to change that, I don't recreate it in a new location in my brain. I just go back to the original location and just update the value that's in there. All right, so that's what we're doing right here. A equals 13. If I then print that out, we'll see that we have a 13 the second time because that's the new value of that. All right, notice it didn't put any spaces there. It's because I didn't do this little end thing if I want to. So that will avoid me having to talk about what that endl thing is for a little bit. So for right now, when you want to kick it down a line, you just tack on \n. That's carriage return line feed. And that'll kick it down a line. So you can read it a little bit cleaner. Otherwise, what it did is it printed something and just left the cursor right there. So the next thing it printed was just right after that. So you can put little spaces or whatever as you're testing stuff. I'll be throwing some additional things at you that allow you to format a little bit better. But for right now, we're really trying to reveal the memory asking questions repetition stuff. All right. Then I think we wrote like an if statement last time. I think we had something like int age is equal to 21. And then we said if age is greater than or equal to 21, then we're going to do something. So now we're asking a question. Syntax for asking a question, just so we get it in the notes. So this is an if statement. This is asking questions. Is if, and it is always case sensitive. So a little bit, Keynote always wants to capitalize stuff. If, then we have something called a Boolean expression, followed by an opening curly brace, 0 or more statements. closing curly brace. And then optionally, you can have an else. 0 more statements. You don't have to have an else. You could just say, if something is true, do this. Otherwise, do nothing. You don't have to give it a secondary thing. So effectively, an if statement is like a blocking. You stop and ask a question, you know, like if it's hot outside, you know, if it's above 70 degrees, don't grab my coat. So you might say, if temperature outside is less than 70, grab coat. If it's not, you're not doing anything else. You're just not going to grab the coat. Make sense? So that's a question we might ask where there isn't an alternative. We're going to do something only under a certain condition. Otherwise, we'll just move on with life. All right. So you don't always need an else with an if. So you at the very least need this part of it. All right. And I am going to talk about the curly brace thing here eventually. So if you're somebody who has had some programming experience, something that, you know, you've maybe seen some code or written some code that didn't have an opening and closing curly brace, is technically, if we're writing this formally, it's if Boolean expression statement, else statement. So this is from a language development perspective. A statement in a programming language is something that is part of the syntax of that language. So you can have a single line of code. So for example, that is a single statement. But if you want to have multiple lines of code, you only get one statement after an if statement. So if you want to do multiple things, you have to put it inside those curly braces. It kind of creates like a collection of statements. So open and closing curly braces are called, that's called a block statement. All right. And inside that block statement, you can have as many statements as you want. Now, what I'm telling you is it is never, ever, 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 ever wrong to just have the thing that always follows your if statement be a block statement. And if you happen to only put one line in there, it's not the end of the world. Okay? So you'll never be wrong if you always have an opening, closing parenthesis, or opening, closing curly brace. But you could sometimes be wrong if you don't. And I'll show that to you here. So we'll go ahead and say, we'll leave the curly braces out for a second. We'll say, see out, have a drink. And I could actually go ahead and put that /n inside there. It's anything with a backslash before it. It's called an escape character. It won't show up on the screen. It just means something to the terminal behind the scenes. So for right now, just do that or do what I did up here just for formatting to get your stuff to kick down a line. You'll do this enough times, it'll just become second nature. This is not something I'll test you on. It's more so you can read the output of your program relatively conveniently. All right. And then I could also have a, let's do, we'll just throw another hello world in here just for the example. All right. So our code currently looks like that. If age is greater than or equal to 21, we intend to say that. Okay. Now, some people, this is just indentation, which isn't important in C++ or C# or Java. It is important in Python, unimportant right here. But just because these two lines look like they're part of this if statement, only this first statement is, because that is the syntax of the if statement. All right. So when I run this and I have age is greater or equal to 21, it's going to say have a drink, and then it's going to say hello world. All right. And right now my age is 21. So we have our have a drink and then hello world. No problem. Well, now we're going to change our age to 15. we're going to ask the question, is 15, so age will resolve to the value that we've remembered, which is 15. Is 15 greater than or equal to 21? It's not, so this is false. Our expectation, the way we have it laid out here is, oh, then it's not going to show any of that. Because visually, it looks like these two lines are part of this if statement. We've tricked ourselves by indenting it. All right. So it looks to us like those two lines are part of that if statement. But when we run this, this guy is false. So the single statement associated with the if statement will not fire. This only fires if this is true. But the second line will fire because it's not actually part of the if statement. It's just a line sitting in the middle of your program. So it's still going to say hello world. That makes sense? So if you want to make it look like it's disconnected, you can do that. You kick it down a line, whatever. Now maybe it looks like it's less attached to the if statement visually, but really from C++'s perspective, it's identical. C++ is perfectly happy with you putting your whole program on one line. Indentation is something for our eyes only. All right. Now let's say that your intention though was to only have the hello world show up when we get into this if statement. If we want to accomplish that, we're going to have to use a block statement, because an if statement is followed by only a single statement, and a block statement counts as one statement no matter how many things I put inside of that block statement. Make sense? So now the two things will happen. So if I hit a run now, it's 15. Is 15 greater or equal to 21? It is not. So we will not get into those statements. We're asking a question, it fails the test, and we don't do what's inside those statements. So we will not see the have a drink or the hello world. Make sense? All right. So what I'm telling you is, it is never, ever, ever wrong to have the opening and closing curly braces. Even if I don't intend to have the hello world in there, and I instead just want that to always show up like this. This still works just fine. Yes, I only have one statement. Technically, the curly braces were not required. But if you just put it in your head that whenever you create an if statement, you give yourself an opening and closing curly brace, and then whatever you want to have happen when the if statement is true, you put in there, you'll never be wrong. Make sense? You're only costing yourself 2 extra lines of code, and it's just one symbol per line. Little hint, nobody's impressed when your program is shorter but doesn't work. Make sense? So you're not trying to write the most concise computer program. You want it to be accurate for you first. So it would make every single effort to do things that reduce how error prone you are. Because I promise most of you are going to be very error prone early on. Okay? So anything you can do to play defense against that will be beneficial to you. And then over time, as you become more versed as a programmer, you get more experience, you'll get your own little tendencies, or you might decide, oh, I don't like the extra curly braces or something, and when I don't need them, I won't put them there. Well, then it's on you. If once you're experienced enough to know that that's the way you like it, then it's just a writing style type thing. Something you'll often see in books is you'll see the if statement written like that, with the opening curly brace up on the same line as the if statement. I mentioned just a minute ago that C++ does not care if I write my entire program on one line. So I don't have to add any of these carriage returns in here. I can just have one gigantic line, and that's my program. C++ is perfectly happy with it. I won't be, because I have to read it when you give me your code, okay? And you're probably not going to be, because you have to read it when you're debugging your code and the 4,000 errors you're getting, okay? So make an effort to format your code kind of like this. IDEs like Online GDB help you with this, right? They auto-indent some stuff. You probably noticed it. So it tries to give you relatively clean code. That will only benefit you. because the more structured your code looks, the easier it'll be for you to see where things begin and end. I don't personally like this format where the curly brace starts in that top line. I think it makes more sense here, where you can see where it begins and where it ends, and notice it even draws a little line between them. Because when you're debugging a program, it's going to be kind of a common mistake that you might want something to be part of this if statement, but maybe you have 100 lines of code, something like that. And you didn't encapsulate that guy inside of that last curly brace just because everything was going on. You made it's not a syntax error, so your program will run. It just won't necessarily do what you want it to do because something you were expecting to happen only inside that if statement is now happening every time. All right. So I think this helps you see when an if statement begins and ends. Similarly, when we look at loops here in a few minutes, same thing's true. It's going to let you see where it begins and ends. So you'll know, oh, I actually need this to be inside of that opening and closing curly brace. I'm not going to take off points if you do something like that. I'm just telling you, I've been doing this for a while, and this format is the better format. Now, one interesting thing you'll find, though, is when you get into industry, a lot of places have coding standards, and some of them will have the other thing as their coding standard. So you'll just have to adapt. The reality is this is left over from a long time ago. Why do you think it became common for the opening curly brace to be on the same line as the if statement? Go ahead. Save space. These used to be in books. Still, you can find it in books, but now if you're on the internet and you have an infinitely long page, it doesn't matter if you have an extra line with a starting curly brace. But when you used to have to squeeze the program onto a single page in a printed book, saving one line was important, right? So something that was done out of a necessity to fit it into a book has now become kind of a standard because people were copying code out of the books as a starting point for their programs, and that just now became a kind of a standard, which I think is a bad standard. Go ahead.
So if you don't put the blocks, you're
Correct. Yep, that's a good way of putting it. If you don't put those opening curly braces, that if statement only impacts the very next line. But I would probably say a good rule of thumb is never write an if statement that isn't immediately followed by the curly braces, the block statement. It's like building a sandwich. If statement, open and closing curly brace, then put whatever stuff you're going to put in the middle in there. Okay? Don't leave the bread off. This is the punchline. And I'm not going to test you on something like that. I'm trying to tell you caveats that you're going to run into programming, because this isn't, I mean, technically those curly braces are not required if you only have one line. It's never going to be wrong. All right. And I think it makes the program look easier to read, and certainly makes it look cooler. Curly braces just look codey, right? All right. So questions about remembering some stuff at the entry level and then asking a question. We're good with that? All right. And we could always do our, so this is where maybe a better example of this thing. Maybe the barkeep says, get out. If you're walking in and you're underage, well, if I start age off at 15 and I run this, it's going to say get out. And we might now be tricked into thinking that, oh, my code is working. But if I change this to 23, now it's going to say have a drink as well as get out. Because this get out here is not associated with this if statement. So it happens every single time, regardless of what happens in here. If we only want to have it happen as an alternative to this if statement, we would put this inside of an else. And an else follows the same rules as the if. The curly braces are not required, but I would say they're Littman required. I'm not going to take off points, but promise you it's the better format. Always put the curly braces, you'll never be wrong. All right. So now If this is 23, is 23 greater than or equal to 21? It is, so it's only going to say this. It will not execute this. It's only one or the other in an if statement. If this is true, do this stuff, else do this stuff. Okay, so now we'll get the have a drink. And if I switch this back to that, now it'll say get out. Make sense? All right, so that's our asking questions. So we got 2 of the 3 out of the way already. Okay, going back to this guy. So now we need to look at repetition. Repetition, I kind of broke into 2 parts. Historically, when you think about repetition in programming, we're thinking about loops. Okay, we're thinking about things that we want to repeat over and over and over again. All right, because we certainly don't want to have to write a program that is 10,000 lines of code where it's kind of like almost like a choose your own adventure book, where everything's an if statement, where it just kind of bounces around based on this. Sometimes you might say, oh, if you've made this decision, I might have 1,000 lines of code that I want you to do. And maybe we put that inside of a loop, so those things happen multiple times in case you go down the wrong road or something like that and have to come back, that kind of thing. All right. Similarly with functions, we might want to do things that are repeatable as well, and we'll look at that. All right. So with repetition, we have something called loops. All right. So there really are 3 different kinds of loops in all of our C-based languages. There's actually a little bit more than that now because we have these things called for each loops, but let's just look at the base 3. Okay, we have a while loop, we have a for loop, and we have a do while loop. All right, first statement I'll say is you can accomplish anything that you would do in a loop using any of these 3 loops, possibly with the assistance of an if statement or something like that in the case of the do while loop. While loops and for loops are very similar to each other. But now what I'm going to tell you here is that each of these loops kind of lends themselves to a certain kind of problem. Okay? So while loops lend themselves to problems where we do not know how many times we will repeat. Basically saying, keep doing this as long as this Boolean expression is true. Make sense? And we don't know when this is going to fail. You can almost say, press any key to continue. Do we know how long it's going to be until the user hits a key? Probably not. So we're just going to have it sit there and spin until they finally hit a key. And then it releases them from that loop. Probably not the way we'd write that today, but historically we would have done that as a busy wait while loop. For loops lend themselves to problems where we know how many times we need to repeat. All right, so maybe if we're counting from 1 to 10, we know we need to do something 10 times. Make sense? So for loops lend themselves to that. That doesn't mean we couldn't write that with a while loop, and I'll show you that here in a few minutes. Do while loops are kind of a funny animal because they're the rarest loop that you'll write, but they're also a loop that as a computer user, you experience every single day. So do while loops lend themselves to problems where the body of the loop must execute at least once. I'll just put up here, body executes 0 or more times for while loops and for loops. All right, so while loops and for loops are what are known as pre-check loops. We check the Boolean condition before we execute the body of the loop even the very first time. So there is a chance with a while loop or a for loop, we will never do the stuff. if it fails the test the first time through. But with a do while loop, we do whatever is in the body of the loop first, then we ask the question. So it'll always happen at least one time. Make sense? Now, I mentioned that this is something all of you experience on a daily basis, whether you know it or not, because your computers are automatically doing this. But every single day, how many of you checked your email today? Most of you, right? Okay. Well, in order to check your email, at some point when it authenticated with Concordia's email servers or Gmail or whatever it was, it had to send your username and password, right? It had to send the username and password once. So it had to check your credentials at least once. And only if you gave it a bad username and or password did it loop back up and ask you again. But you had to give it to it one time, at least. Make sense? So it's kind of an interesting irony that a do while loop will be the rarest loop you ever write, yet it's something that every program that we typically work with that has authentication in it will have. It's going to keep asking you for your username and password till you get it right. Maybe there's a little counter in there after you've tried 7 times and it yells at you and said you've tried too many times, we've locked you out or whatever, but you know, that's the nature of the loop. All right, so we're going to back burner the do while loop for a little bit here because really your bread and butter loops are going to be the while loop and the for loop. All right, so let's look at these through some examples that kind of show the what they lend themselves to, but also show that they both can solve the same problems and why you might choose one over the other. And I'll because we're going to be talking about something called variable scope. All right. So I'm just going to get rid of some of that stuff here. And we're going to write a while loop. So let's just count from 1 to 10. All right. So initially, I mentioned that while loops lend themselves to problems that where you don't know how many times you need to loop. Well, if I'm counting from 1 to 10, we know exactly how many times we need to loop. But I'm still going to use a while loop to do this so we can compare it to a for loop. So I'm going to say int count is equal to 0. I said 1 to 10, right? Int count starts off at 1. While count is less than or equal to 10. We're going to do some stuff. What are we going to do? We're going to say cout count. And then we're going to say count is equal to count plus 1. So remember, while loops are pre-check loops, which means we will test this Boolean expression the very first time before we do anything inside the loop. So we're remembering something here. We're remembering a variable named count. We're starting it off at the value 1. We come to the while loop. We ask ourselves, is the current value of count, is it less than or equal to 10? Current value of count is 1. Is 1 less than or equal to 10? Yeah, 1's less than or equal to 10. So what are we going to do? We are going to print out the current value of count, which resolves to 1. Then we'll press enter, kick it down a line. And then we're going to update the value of count. So in this case, this single equal sign here is the assignment operator. We've already seen it, but let me just throw that out there. This is the assignment operator. Assigns the value on the right-hand side to the variable on the left-hand side. So for example, age is equal to 13, something like that. So whatever this value is over here, we're assigning it to this variable that's sitting over here. That's when we use the assignment operator. When we are finding out whether something is equivalent, we use the double equal sign. I'll show you that here in a few minutes. So that's why it's important to understand the difference between a single equal sign and a double equal sign. Double equal sign allows us to ask the question, is your age equal to 15? We use a double equal sign for that. That's asking a Boolean, and it's a Boolean expression. It's a Boolean operator. Single equal sign is just assigning one value into a variable. Okay. So what are we doing here? We are updating the value of count. What are we updating it to? We are assigning it to whatever the current value of count is, which is 1, plus 1. So this will change count's value to 2. Then we hit the end of the loop. And because this is a loop, instead of an if statement, we will spin back up and ask the question again. So we ask, is the current value of count, which is now 2, is that less than or equal to 10? Still is. We'll print out a 2. 2 becomes 3. Spin back up. Is 3 less than or equal to 10? Yada, 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 yada. Now it's a 10. Is 10 less than or equal to 10? It is. It's going to be our last pass through. So we'll print out a 10. 10 becomes an 11. We spin back up. Is 11 the current value of count? Is that less than or equal to 10? It is not. So this loop dies right there and then. And we will not do the body. We will not execute the body another time. And we'll just drop right past it. And I'll just do like a C out. Loop is done. Something like that, just to give us some visual feedback. All right. So we expect this program to print to the screen 1 to 10. Followed by loop is done. So there's our 1 to 10. Got to scroll up sometimes to see it, or you can expand that, but whatever. All right, makes some sense? Now the power of this is, what if I wanted to do this 100,000 times? I just changed one number, and now all of a sudden I'm going to be repeating something 100,000 times. A human being can do something 10 times. We might start getting annoyed because that starts feeling like a little kind of repetitive. But 100,000 times, we're out the door. That's computer work, right? So now we're starting to see what we might rely on a computer to do when we can describe an algorithm. Say, I want you to do these same 8 steps, for example, 100,000 times, 1,000,000 times, 100 million times. Things that a human being wouldn't even consider doing, but we can have a computer do it for us because that's what it's good at. All right, so I didn't change anything in the logic, and now it does it. What did I do? 100,000? 100,000 times. Now I'm going to show you an interesting thing here. This is something to stick in the back of your head. This is more of an operating systems concept. Okay, so you saw how long that took, right? I'm going to do one last little thing here. I'm going to say C out count. Yeah. So I'm going to just have count display one last time after the loop. So we should see it sitting there at 100,001, right? Because that's what finally made the loop fail. So I'm going to run this one more time just for completeness here. So it's going to take whatever the 15 seconds or so for it to run through. And we'll end up with 100,001 right before the loop is done. This did not go through the body of the loop. This is this condition where it failed, right? Okay. Now, what did that take? 10, 15 seconds to run? I'm just going to comment out this one line. 2 little slashes before it says, human eyes only, don't actually execute this. All right. So I'm still taking count on a voyage between 1 and 100,000. My variable is still changing 100,000 times. Watch how fast this runs. What does that tell you? Printing to the screen is expensive. So if you're going to display something to the screen 100,000 times, even if the math you're doing behind the scenes is super trivial, every single time you ask the operating system to show something on the screen. Remember the assembly code we looked at, the Linux Hello World program? And we were using that syswrite system call to tell the operating system to put something on the screen for us. Behind the scenes there, that is expensive because there is a whole separate subsystem of your computer that actually talks to your monitor, okay? that isn't your program, that doesn't involve your processor. So every single time we went through this loop, every single time we changed the value of count, we then had to tell our processor, hold on, I can't use you again until after I talk to the operating system to display something to the screen. Then I'll come back, get back in line to use the processor to add 1 to my variable, and then I'll put you on hold again to go over and talk to the monitor, come back, get in line, add 1, get out of line, talk to the monitor, yada, 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 yada. These are called context switches. You'll learn about this in CSC200, the operating systems class. It's expensive. You wait in line. Our computers are really fast today. We talked about multiple core processors where you can technically do more than one thing at once. But if we just use our example here with a single core processor, because it helps with this example, that means at any point in time, our computer can only do one thing at once. But we rely on the fact that computers are really, really, really fast. And since computers are really fast, we can have the computer doing a whole bunch of stuff in sequence, yet the human being is tricked into thinking it's all happening at the same time, right? Because of how fast it's happening. But is it very efficient for something? Because usually one of the things you'll learn in the operating systems class as well is how does the operating system schedule for that processor? How much time does one of your 5 programs you have open on your computer, how much time does each one get on the processor before it's the next one's turn in order to make sure that the human being is properly tricked, right? That we think everything's happening at once, all right? Because all this is happening behind the scenes. And let's just use a human measurable time period. Let's say that every single program gets 1 second on the processor. It gets far less than that. Let's just say 1 second. All right. And I promise you a computer can do a lot of stuff in 1 second. Billions of instructions in 1 second. Those magic tricks on the CPU. All right. So if every 1 second we are taking whatever's currently on the CPU, telling it to get back in the end of the line so that the next person can get up and get some CPU time, we're using our processor as efficiently as the operating system has deemed it, since it's saying we've set aside 1 second little blocks of time where you get to use the resource, the CPU. But in this case, if I'm telling you that a computer can do 1 billion things in a second, and we're only doing one thing, that means we are wasting 99%, well, 99.9% of our billion instructions because we didn't use our whole allotted time. We did one thing and then we said, oh, I'm done. And then we left, only to get back in line. And it's expensive you got to look at it kind of like unpacking your bags and packing your bags. You know, since we have computer programs coming onto the processor and they accomplish as much as they can accomplish within that 1 second, once they're done, they have to kind of remember where they left off. So they can go get back in line, and when they get back onto the processor, they can pick up where they left off, right? So they have to remember the current state of all the hardware registers, the current state of the CPU that program takes with it when it leaves the processor and then unpacks it when it gets onto the processor. That's a context switch. It takes time. And we're experiencing that time when we just watch that program run, printing out something each line, because we're seeing the evidence of it leaving the processor, getting in line, coming back to the processor. And clearly a program ran way, 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 way slower, right? All right. Not the end of the world, 15 seconds, whatever, but extrapolate that off of something more. If I set this to 2.1 billion, which is the largest value one of our integers can hold, it's going to be running for a while, right? It'd be an interesting math problem. We can do the math on it and find out, but it wouldn't finish by the end of class. I'm guessing, just in my head, I think it would probably finish somewhere in the middle of the night, but I might be way off. And the numbers might get so big there, we're talking about like a week or something. And we'll run into some interesting problems like that, where we have to look at, we might have an algorithm that works, but it's very inefficient. And under certain circumstances, the efficiency of it becomes noticeable. A famous problem that feels trivial to us that's like that is Remember fractions? What grade did we learn fractions in? Like third grade? Something like that. And you remember reducing fractions? Like 4/6 is 2/3. Now, does it feel like reducing a fraction is a really hard thing for a computer to do? That seems like a pretty easy thing, right? Okay. And it is in small little pieces, because when you're reducing a fraction, what are you doing? You're finding the greatest common divisor of both the numerator and the denominator. What is the biggest value that evenly divides both the numerator and the denominator? And as a human being, you might say, okay, well, I'll start off by looking at the numerator and the denominator, and I'm going to say, well, which of those is smaller? Because whichever of those is smaller, that's the biggest value that could possibly evenly divide both of them, right? You might be able to look at it and say, well, it's only a little bit smaller, so really it's got to be a lot smaller than that in order to possibly do it. But if we're just being really just, by the book here, if we have 4/6, we'll say the biggest number that can possibly divide both values is 4. Does 4 divide 4? Yes. Does 4 divide 6? No. Does 3 divide 4? No. Does 3 divide 6? Yes. We got to find one that divides both of them, right? Does 2 divide 4? Yes. Does 2 divide 6? Yes. Ding, 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 ding. We have our greatest common divisor. So then you divide the numerator by 2, you divide the denominator by 2, poof, you have a reduced fraction. That seems like something pretty easy for a computer to do, given that we just saw it run through 100,000 numbers in no time whatsoever, as long as we weren't printing, right? That's what makes that problem a fun problem, because actually reducing fractions is extremely expensive for a computer. We just used a tiny example that is not hard for a computer. But imagine what happens as your numerators and your denominators get larger. Because effectively what we just did is we used a brute force approach, right? We took whatever the smaller of our two numbers, and let's assume those two numbers are both giant numbers. Let's say they were longs. So each number is between 0 and what do we say, 9.2 quintillion. Big number, right? And let's say that the numerator was only 1 smaller than the denominator, right? We're at the 9.2 quintillion on the numerator and 9.2 minus 1 quintillion as the denominator. How long would it take to count down from 9.2 quintillion till you got to a number that evenly divided both the numerator and the denominator, considering that every single time through we said, does this giant number evenly divide this guy and evenly divide this guy? Nope, try the next gigantic number, so on and so forth. Start seeing the problem? 9.2 quintillion times a lot of times. That program could take months and months to run. We don't think about it like that because we don't typically think about it at that scale. Well, there exists an algorithm for finding the greatest common divisor that will make that program that might take a month to run in a second. And it's a famous algorithm. Anybody know what the name of the algorithm is? You maybe learned about it in high school, one of your high school math classes. It's called the Euclidean algorithm for greatest common divisor. And the funny thing is, it's like 5 lines of code. So 5 lines of code, simple code. Well, it's mathy, but I mean, it's like divide this number by, this other number and then replace this number with this one. It's not hard math. It's just like 4 or 5 lines of small little math things. Yet it will make that program run in a second versus a month, making that tiny little change. So every now and then you'll bump into time complexity problems like that. And those are always the most frustrating. And they get more and more frustrating as our computers get faster and faster, because we have this mentality that our computers are basically infinitely fast, right? And the reality is, for 99.9% of the problems we solve, they are. You can solve the problem the most inefficient correct way versus the most efficient correct way. And to a human being, they would not be able to tell the difference 99.9% of the time, because your computer is so fast, it's just going to run in a blink of the eye. But every now and then, you run into those frustrating problems where now you're hunting in your program, where did I introduce an infinite loop? because clearly my program's not working, even though it actually was. It was just going through 9.2 quintillion checks till I finally found a number. It was really working hard in the background. And you'll know after a few minutes when your fan starts spinning up on your computer, and it's like, okay, these dude's definitely working. All right, and you start burning your lap or whatever. But just keep that in the back of your mind. And I'm telling, other than me forcing it upon you at some point, we'll look at that example. But other than that, you might go through possibly your whole career and never run into one of those problems. Okay, so it's not something that you need to, be overly worried about, but just tuck it away somewhere back there, that every now and then there could be a problem that you do actually have to put a little bit more thought into from a mathy perspective, where you actually do have to optimize it to accomplish something in a more reasonable amount of time or something like that. We see a lot of those things like in video games, where there's a lot of explosions and things happening on the screen, where we really are taxing the system. And maybe there's one aspect of the game that just really needs to be responsive, for example. And the difference between an eighth of a second and a 16th of a second is noticeable. It always amazes me. It's not something I notice, but like if you take somebody who's like a really good gamer, like competitive type gamer, and you see these TVs that are monitors that are designed for gaming, right? 240 hertz monitors, for example. A 240 hertz monitor that basically says it can show 240 pictures every second. Because that's what a video is, right? It's just a whole bunch of pictures shown right after each other. So if we watch a movie, a lot of times those are 24 frames a second. Okay. Now, the higher format movies, they maybe run at like 60 frames a second. The human eye can notice somewhere in like the 40, 44 frames a second range. So you might say, well, why do we have to have anything that can show faster than, well, let's just round up. We'll say, why do we need to have anything that shows more than 50 frames a second if that's all our eye can see? Well, because just because your eye isn't really identifying it, you do feel it. And if you talk to any gamer, if they would be able to tell the difference between somebody running at 60 frames a second versus somebody running at 240 frames a second. There's some little almost indistinguishable level of smoothness that occurs there that you can't really explain, that your eye isn't really detecting noticeably, but it's happening. Something like that. All right. So sometimes optimizations are important, but like I said, 99% of the time, 99.9% of the time, this will not be something that you have to worry about. Just tuck it in the back of your head, because at some point in your career, you might bump into one of those problems. Okay. But for now, your rule of thumb would be, when you're solving a problem, solve it in the way that makes the most sense to you. Don't worry about whether it's the most efficient or whether it's the shortest lines of code. If you like creating 5 different variables for something and then using those 5 variables, even if after the fact you realize, oh, I didn't need so many variables, but if you prefer that, you like saying, okay, I'm going to remember these 5 things, and then I'm going to use those 5 things that I remembered. If you like that thing and it makes the most sense to you, do that. Because a inefficient, whether it's speed inefficiency or memory inefficiency, isn't going to make any difference to our computers today. And I'd much rather you have an accurate answer that you understand than you trying to take some kind of shortcut because you think I want to see less code, or I want to see it more optimized. And now you've made mistakes. Do it in the way that makes the most sense to you. And over time, you are a smart human being. You will figure out your own little shortcuts that you're comfortable with. Okay. So kind of take that as a rule of thumb. Don't worry about efficiency until you have to. And most of you may never have to in your whole career, because computers are going to keep getting faster and faster, and they're already fast enough. All right. So questions on this while loop. All right, so let's take this back down to 10 so it runs relatively quickly for us again. All right, so now what I'm going to do is I'm going to write the same loop a second time. So just for, I'll use this to show you a multi-line comment. All right, so I want this entire block of code here to be ignored for right now. So what you can do is you can do a front slash asterisk before it, then an asterisk front slash afterwards, and anything in between those will be ignored. So I'm just kind of putting that code on hold for the moment so I can rewrite the same code, functionally the same code as a for loop. Okay. I'm going to say for int, I'm going to say I instead of count, and I'll explain why in a minute, equals 1. I is less than or equal to 10. I is equal to I plus 1. C out I. All right. So that's going to take us, it's going to print out the numbers 1 through 10. Let's go ahead and run that guy. So there's our 1 through 10 as a for loop. So that's just that code right there running. So the first thing we might notice is, oh, well, that code looks a little bit more concise. A couple lines shorter. Again, that doesn't matter. Nobody's impressed if you've written something in 3 lines of code rather than 7 lines of code, if it still works. And these guys might seem like they are equivalent, but they're not quite identically equivalent. And let me show you that up here. Here, I'll keep them as the loop is done. So I'm going to run the same code 2 different times. Notice I've taken this line out for right now. And we're going to see right now, the output is identical. First one is 1 through 10, followed by loop is done. Second one is 1 through 10, followed by loop is done. So far, so good. All right, output is identical. All right, so now I'm going to go ahead and put that line back in. What do we expect this line to print out in this example? Start off at a 1, went to a 2, a 3, a 4. Is 10 less than or equal to 10? Yes. Is 11 less than or equal to 10? Nope. We fall past. What's going to print out? It's going to print out an 11. The value where our loop finally failed. So there's our 11 right there. Okay. So I'm going to take the same thing. Actually, I could just use this line. And I'm going to put it right here after the for loop. What do we expect to print out there? Also an 11, we might think, right? We get an error. It says, I was not declared in this scope. Okay. One skill you're going to learn, whether you want to or not, because the number of errors you're going to end up getting when you're writing your code, is how to read error messages. So first rule of thumb, when you get an error like this, actually read the message. Now, the message may be very, very, very good in that it points you to the exact place. So notice here, it's yelling about something on line 30. And at this point in time, the problem is on line 30. But you might run into an error where you get an error message and it says the error was on line 30, but it could have been from something that you brought into existence on line 5. Okay, so you're going to have to learn that skill of debugging your program and working backwards from when your program first freaked out. Make sense? Okay. Because notice that this did not happen until I ran it. All right. Because it wasn't, well, in this case, it happened before I ran it because it was a syntax error in that I wrote legal code, but it's code that will never work because in this case, something called the scope. Let's talk about variable scope. So variable scope is the part of the program where a variable is accessible. We can say as a general rule, every set of curly braces comes with its own scope. That actually is not a 100% truth across the entire language, but it's a 98% truth. There are a couple of curly brace based structures where they don't actually come with their own scope. I'm not going to go into that at this point. We'll run into some of those, but for right now, you can basically say whenever you see curly braces, a new scope was born. Okay. Now, what does that mean for us out in our program here? Well, I see a set of curly braces here for main, right? So one scope exists with everything that's highlighted there. Okay. So if a variable like count here was defined on this line, it's accessible anywhere inside of that scope from that line forward. You couldn't use it before it was defined, but starting on line 17, you could start using count. And you can use it anywhere inside the curly braces where it was defined. Make sense? Even inside of other curly braces. So now we have this guy right here. And when I say curly braces, really it's the whole structure those curly braces are attached to. So that means anything that we had defined inside this while loop lives and dies with the while loop. Similarly, anything we define inside the for loop lives and dies with the for loop. This while loop is operating on a variable called count. Yet, count was defined outside of the while loop, but inside main. Therefore, not only do we have access to it inside the while loop, we also have access to it outside of the while loop. Whereas this for loop, I was defined inside the loop. So its entire life cycle lives right there. It was born inside the loop. It died when the loop ended. So when we got to this line right here, it said, I've never heard of I. Because I died at the end of that for loop. Does that make sense? So a little tiny difference, but a lot of times when we're writing for loops are very common. And the reason I used an I here, I know we're out of time. Let me just finish this thought. We used an I here, is I is kind of like a throwaway variable. One thing we're going to be talking about is making sure we name our variables meaningful things. But in this case, I'm just saying I want to count from 1 to 10. That's not like storing your age or your name or the value of pi, right? This is like, I want to count for a few minutes, and when I'm done counting, this variable is gone as far as I'm concerned. This allows us to use I multiple times in our program for counting. Okay, so I'm going to put a homework assignment up. What I'm going to have you do is, and I'll give you this as a starting point, just so you have some example code. I'm going to have you basically do like a countdown. So you'll have to modify the code slightly to count backwards. All right. Again, I promise you they're going to get harder. So take the respite when you got it, but I want you to get used to making your typos and those kind of things. Okay. So I'm going to have you count down from like 10 to 0 for like a rocket launch or something. Okay. I'll put that up here in a few minutes. I will see everybody on Thursday. And for those of you who are doing the hackathon tonight, have fun with that. I'm looking forward to hearing feedback. Even if it's bad feedback, tell me and tell Ross so we can improve it. Next time, there's always room to make things better, right?
Question.
Sure.
So would those hackathons be beneficial for my major